Hello, so I'm going to be presenting chapter 6 of the book. So chapter 6 is talk about ensemble methods. So the content of this presentation is as follows. First, introduction, then bootstrap aggregation algorithm, then a little bit of talking about variance reduction, then the accuracy of the bootstrap algorithm, then observation redundancy, random forest, boosting algorithm, then bagging versus boosting in finance, and finally bagging for scalability. Okay, so introduction. In this presentation I will present two of the most famous ensemble models, which are bootstrap aggregation, also known as bagging, and also the boosting algorithm. The three sources of error in a machine learning algorithms are the following. We have first the bias. When the bias is high, the machine learning model does not generalize well. It failed to capture the distribution of the training dataset. The model underfit when the bias is high. And we have the variance. The variance, this error is caused by sensitivity to a slight change in the training dataset. When the variance is high, the machine learning model overfit. The model has mistaken noise with signal. And we have the noise. The noise is caused by unpredictable changes and measurement error. It cannot be explained by any model. We have the following formula of the mean squared error. So the first term right here corresponds to the bias. The second is the variance, and the last term corresponds to the noise. Bootstrap aggregation, aka bagging. Okay, so an ensemble method combines a set of weak learners, all based on the same learning algorithm, for example, decision trees, in order to create a stronger learner, better performing than the individual ones. And that can help reduce the bias and or the variance. So the bootstrap aggregation is an ensemble method that helps reducing the variance, overfitting. It is extensively used on decision trees models, which are known to overfit. The algorithms work as follows. First, generate n training dataset by random sampling with replacement, also known as bootstrapping. Fit n estimator, one for each training set. The model are trained independently of each other, meaning that the procedure can be done in parallel. Then, the ensemble prediction is simply the average of individual forecasts of the n models. In the case of a classification problem, we use the majority voting to get the ensemble models prediction. Or we just average the probabilities predicted by the n models to get the ensemble model predicted probability of belonging to a particular class. Variance reduction. So a big advantage of the bagging algorithm is reducing the variance of the n classifier, meaning it reduces overfitting. So we can prove the following formula of the variance of the ensemble. So we have the covariances between the estimators is given by this, and this implies that the total variance of the ensemble method is equal to this, where sigma bar square is the mean variance of each estimator. Okay, so this seems to reduce the variance when rho bar is inferior than 1, which is the correlation coefficient. In the extreme case where rho bar is almost equal to 1, the variance of the ensemble bagged model correspond to a single base model, meaning there is no improvement in variance of our model. Bootstrapping goals is to produce samples that are independent as possible in order to reduce the variance. Improved accuracy. So considering a bagging classifier that makes a prediction on K class by majority voting among n independent classifier, we label prediction as 0, 1, where 1 means correct prediction. The accuracy of a classifier is the probability P of labeling a prediction as 1. On average, we will get n multiplied by p prediction labeled as 1 with a variance of n multiplied by p multiplied by n minus p, 1 minus p, which follow a binomial distribution. Majority voting makes the correct prediction when the most forecasted class is observed. For example, if the sample size is equal to 10 and K class, we have 3 classes, the bagging classifier made a correct prediction when class A was observed and the cast votes were 4 for class A. However, the bagging classifier made an incorrect prediction when class A was observed and the cast votes were 5 for class C. So we have a sufficient condition is that the sum of these labels, which we call X, needs to be superior than n divided by 2. A necessary but non-sufficient condition is that X needs to be superior than n divided by K, which occur with probability. We have this probability here using the binomial distribution. This is the absolute value of this fraction n over K. So using this exponential inequality and the Hoeffding inequality right here, we can prove that the probability of X being superior than n divided by Q is superior than P when the sample size is superior than this value. So for a sufficient large sample size, such as n superior than this value, we are sure to have this probability superior than the probability of a single classifier, meaning that the bagging model do improve accuracy as the bagging classifier accuracy exceeds the average accuracy of the individual classifier. Observation redundancy. In general, financial observation cannot be assumed to be independent. The effect of redundant observation on bagging is that the bootstrapped samples are most likely to be identical, even while not sharing the same observation, meaning that we have a correlation coefficient close to 1. This means bagging will not reduce the variance regardless of the number of estimator n, as the variance of the ensemble model will be almost equal to the average variance of a single model. Out-of-bag samples are observation not included, left out in the bootstrap sample, and hence not used in the training of the estimator. So this out-of-bag sample can be used to assess the accuracy of the estimator. But in financial observation cannot be independent, identically distributed. So out-of-the-bag accuracy will be inflated. Random forest. A random forest algorithm. As stated before, decision tree usually overfit. They have a high variance. In order to address this concern, the random forest algorithm was introduced with a goal of lowering the variance of our model. Like bagging, random forest reduce variance as long as the correlation coefficient is inferior than 1. It shares some similarity with bagging, except that while building each of the n models, only a smaller sample without replacement of feature is used for each split. The size of feature samples is usually taken to be equal to square root of m, where m is the total number of features. This second level of randomness usually yield a lower variance. Its purpose is to further decolorating the estimator. Random forest algorithm can also be used to evaluate the feature importance. Random forests provide out-of-bag accuracy estimator. However, like we said before, in financial application, they are likely to be inflated. Okay, when a number of samples are redundant, non-independent, overfitting will still occur. Bootstrapping, sampling with replacement, will build a large number of essentially identical trees. Random forest fixes the size of the bootstrapping sample to match the size of the original training dataset. Okay, so the following snippet shows 3 ways of setting up a random forest classifier using the sklearn Python library. So we have the first model, which consists of directly calling the random forest classifier method. The second method consists of first building a base decision tree, then using bagging classifier method in order to get a random forest classifier. The third method consists of using random forest classifier first, then with only one classifier. You can see here number of estimator equal to 1. Then using the bagging classifier method in order to obtain a random forest classifier. Okay, so to me, the first method is the most straightforward and recommended. It is also recommended to fit a random forest model on PCA of the feature obtained using principal component analysis, as this reduces the number of level needed by the tree and thus speed up calculation and reduce overfitting. Setting class weight equal balanced subsample in sklearn can help in predicting the minority class. Bootstrapping algorithm. Boosting consists of boosting algorithm. Boosting consists of combining some weak estimator slightly better than random guessing in order to achieve one with high accuracy. Shapir demonstrated that this is possible. Boosting works as follows. First, we generate one training set by random sampling with replacement. Bootstrapping according to some sample weight. The initial weights are uniformly distributed. Then we fit an estimator using the created training set. In the case the estimator performs better than random guess, meaning that it performs better than chance, the estimator is kept, otherwise it is discarded. Fourth, give more weight to misclassified observation and less weight to correctly classified observation. Repeat the previous step with n until we have n estimator produced. And finally, the boosted model prediction are the weighted average of the individual forecasts from the n models, with the weights determined by the accuracy of the individual estimators. The most popular boosting algorithms are AdaBoost, adaptive boosting, and gradient boosting. Boosting versus bagging in finance. Boosting is different than bagging in the following aspects. Individual classifiers are fit sequentially, meaning that parallelization is not possible. We have poor performing classifiers are discarded. The weight given to each observation row change in each iteration. The ensemble prediction is given by a weighted average of the individual learners. Boosting main advantage is that it reduces both bias and variance, but still boosting algorithms are known to reduce bias, which is underfitting. This is of a significant risk of creating some overfitting. In financial application, bagging is generally preferable over boosting as it addresses overfitting. And overfitting is of great concern as it is common to overfitting while using financial data because of the low signal to noise ratio. Another great advantage is that bagging can be parallelized. Bagging for scalability. Many machine learning algorithms do not scale well with the sample size. As an example, support vector machine. While attempting to fit a support vector machine on 1 million of observation, it may take too much time for the model to converge. And even in the case of conversion, we are not sure the achieved minimum of the loss function is a global optimum, or the algorithm did not overfit. A practical approach is to build a bagging algorithm using a base estimator belonging to a class that does not scale well with the sample size. To reduce overfitting, we can use some regulation technique such as early stopping. For example, in scikit-learn support vector machine implementation, we can set a low value for the maximum number of iteration parameter, or we can raise the tolerance level of the parameter tol, which has a default value equal to 10 power minus 3. This will force our early stopping. We can early stop other algorithms as well with equivalent parameter like the number of levels in a random forest, which is max depth. So the bagging algorithm can be parallelized. As we said before, we are transforming a large sequential task into tiny smaller ones that are run simultaneously. Early stopping will increase the bias of the output from the individual base estimator. However, that increase can be offset by the variance reduction associated with the bagging algorithm. The variance reduction can be controlled by increasing the number of independent base estimators. Used on this way, bagging allows to achieve fast and robust estimates on extremely large data sets. Thank you for your attention.